So anyway, I'm going to talk about another aspect of Mike's work, where he worked on changing some of the bars that get used in the state of Virginia. And of course, some of these guys in the front row there, a little bit of work on that too. And but I also spent a lot of time with Mike on other things. So I knew Mike for over 30 years. It's close to 40, but I say over 30 makes me a little younger. And he was always trying to do his best for the Virginia DOT. I would come in. I worked for an admixture company. I was probably a snake oil salesman, coming in the door. But he listened, and he gave his concerns, and we had good discussions. And I've always appreciated that. And like I say, if you came in with a new technology, he didn't get, I think his sounder so rightly put out, he didn't throw you out the door. He just said, okay, show me how it works. Let me see how I can test it and see how it works. So he did a lot of testing, and he did a lot of looking at it. If they worked, he would use it, but only if it made sense for Virginia. Just because it's a fancy new technology, if it wasn't cost effective, it didn't make any sense to do it. So I think he always had the state in his thinking about the state, and I think everybody I know that worked for him really liked him too, which I think is important, because I never heard a bad word about him. I knew him for a long time, and I'm good friends with some of the guys that worked for him, so they would have said something if he wasn't a great guy. He is a great guy. But as also mentioned, he shared his knowledge from participation. He just, sure, he writes, stick in Virginia. A lot of people can stay happy in their company, not do anything. But no, he took an active role in ACI, is why we're having this for him at ACI. And he also was very instrumental in TRB, as mentioned. And I think, this from hearing many of his presentations and talking with him, I learned a lot, and I think that was the best thing about him. He was a great guy, and he made sure other people got a hold of him. And I was shocked a year ago when I found out about him, which most of you probably were. And I'll miss him. He was a great guy, and I don't know if I have time. I don't have time to tell my stories about that, but he was a good storyteller. If anybody knew him, so it was pretty nice. I think one time I actually went to his house to see him. I recall that, and we had a nice discussion about some things. But he set me straight on a couple things too. We were getting into overlays with fibers, and I thought, oh, we get away with a 2-inch. He said, no, you got a 2-inch overlay, the trunk of concrete will come out and hit a car. You got to have at least 3 inches thick when you do that, when you fill those spots. So that was news to me, but it brought that information back home. So like I say, I'll miss him. I think a lot of the people in this room will miss him too. So anyway, let me talk about one of the other aspects of things that work are mitigating the corrosion of steel and concrete, and it's critical to extending the concrete structure service life, and we're using concrete in severe environments. Normally they're de-icing salts or marine salt exposure. Michigan's blessed to have both in some cases. So it's tough. Part of the problem is we use concrete is so durable, we tend to use it in applications that are really stretch its limits. We want several means to extend the corrosion damage. One, you can reduce chloride ingress, increasing concrete cover, which is the easiest thing, and I think we learned our lessons from when we built the interstate highway system. You want the bar near the surface, but not too near the surface, I think is what we learned from that. You want to decrease the permeability of the concrete, and that would be by adding various SCMs, lowering the water cementitious ratios and stuff like that. And then, as we saw on some of the work he's done, you can add membranes and sealers. They also will help. So, there's many methods out there. What we'll be concentrating today is improving the corrosion resistance of the bars. And there's two ways of doing that. One, you can get corrosion-resistant reinforcing bars, which could be through alloying or coatings or a combination of the two. Or you can add corrosion inhibitors to the concrete. And all three of these things have been used in Virginia in various locations. Since I've been in this field, Mike was always there, so I think he had a good say in all of that. Cathodic protection, which I don't think anybody said anything about Mike with that, but he did a lot on cathodic protection, and he had one great paper where he did a survey of what was going on in Virginia, and there was some very somewhat comical, except the fact that it was serious, where things were hooked up backwards. Let's say he was able to find that. So but yeah. So he was in several things. So we're gonna show how you can take the corrosion-resistant bars that we're talking about. You can assess the service life improvements, and usually you can do that. A lot of these systems can be used together. And a lot of places they are. The more severe environment you have, you don't try to do it all with concrete. You don't try to do it all with the bar. You don't try to do, you'll have membranes. You'll have higher performance concretes. You'll have corrosion-resistant rebars. You'll have inhibitors. You'll do the whole kitchen sink, because this is a monumental structure that you can have going on to service. In other cases, it's a little county bridge. You might use one or two of them. It's not as important, but Mike kind of knew where it was important and where it wasn't important, which I think is a good thing. So we're going to do, so today I'm going to concentrate on basically black bar as a comparison and chromium containing alloys for bridge deck. And I guess these are the two new rebars that are currently being used in Virginia, which for depending on the environment, and do some service life predictions, and more importantly, using that to determine economic benefits. Why do you want to spend more money up front to use these things? It's quite apparent what you do this. A lot of the data, I'm not going to go into how all the data got there, but a lot of it's based on our in-house testing and literature values. We use for threshold values, we use slightly lower values for deterministic modeling, which I'm using here, but you can use probabilistic models. Probabilistic models, you can get the chloride threshold to be a little bit higher, because they'll cover the lower values with due to probabilistic distribution of the chloride, the threshold values. And then today I'm using stadium. If people were here in Boston and last fall, we had a session comparing the various models. So you can, if you use the models right and you get the right parameters, they all work. But today I'm just going to concentrate on stadium. So what we're looking at is a black bar we call B black bar, which is this normal carbon steel, A1035, A stem 1035, 9% chrome, and another one that's 4% chrome. And the duplex stainless steel in this case was 2304 for this modeling. But you can do any other, you can put anything you want in there once you know the values of what they do, how they behave. The black bar, you can see the composition, no chrome in it, it's an impurity. You get to the 1035, you can see it's up to 9.5% chrome. In this particular alloy that we looked at, if it got up to above 10%, then we'd be calling it a stainless steel. So it's got to be, it gets below that. And you can see the duplex steel has 22.76% chrome, 23% chrome in it roughly. It's got higher other alloy contents in it. So it's a more expensive alloy to produce. But another, but it does have, obviously, you do get something for the extra materials in there. Now, I'd say I'm using a Midwest bridge deck as a comparison here, because I didn't. This is some of the data I had in hand, but we did samples with Virginia materials and Virginia locations and all over the country, all over the world for that matter. So it doesn't really matter, but because we're trying to show how you go about it. The in-place cost includes cost savings of using less steel for higher grades of strength. And I'll mention it now, and I'll mention a little later on. Those of you who are designing bridges, if you decide up front that you're going to use 1035 steel or the stainless steel, they have higher yield strengths. If you put that into your structural design up front, you can save some money on the cost of building that structure and give it better corrosion protection at the same time. Often they come in, the structural design's all there, and I know why my company does a lot of this, and said, okay, you've got this cover, this concrete, okay, this is what you got to work with. Well, okay, but you can save some money if you use this on design. Now, we don't want to redo the design, but but ideally you really want to think about that. We're looking at using stadium analysis once again to analyze the chloride coming in for 100 years. Based on the various based on the exposure conditions and literature data from, as I mentioned before, from in-house and experiments for chloride initiation values for the reinforcing bars. In some cases, they might be a little bit conservative, but or not conservative, but you can change those as is. So anyways, the first thing we look at is the black bar, and that we're using a grade 60, which is the common one, threshold value of 500 parts per million chloride total in the concrete by mass of the concrete, and the propagation typically 5 to 7 years after corrosion starts. That also came from a sharp study that I worked on with Mike and Richard Wires, where they looked at bridges and took about 5 to 7 years after corrosion started to start seeing cracking and spalling on the surface. So I mean, it might vary from location to location, but that's a good number unless you have local data to say otherwise. And today's prices, it's roughly 75 cents a pound for buying that bar. It might be more or less depending where you're at, but that's roughly the price. Now, if you look at the A1035 with the 4% chrome, it has a higher tensile strength, which I showed before. It's up over, the Neal strengths are much higher, so you can use it as a 60, which is basically the same as the control bar. You end up with a higher threshold value. It's got a little, because it's not as good a cathode. It takes longer for it. The propagation's longer, and the price ends up being on a direct basis. It's $1.36 a pound. However, you start taking advantage of the strength carriers, use it as a 75 or a 100 grade. You now end up with, you still have the same threshold value, but you end up, the equivalent weight of bar mass you have to use drops the price from $1.35 to $1.08 or even 80 cents. So now they're getting very close to the cost of the black bar when you take advantage of the structural performance you can have. And you could be conservative and say, hey, I'm not going to take the 100, I'll just take the 75. Now you got better structural performance, and you save money. If you want to get it all the way down, you can go higher up, but it's the design engineers to decide how they want to do it. But if you take conscious decision of that on the design end, you can do that. On 9 chrome, it's the same general thing. It's because now you're paying for chrome, as you'll see as we move down to the duplex. But I mean, the chrome now it's got the base price for a pound is a little bit higher, and then once again as you start taking advantage of the strength that you can do, the price drops significantly. And once again, starts getting they're more than the black bar, but it starts getting close to it. The stainless steel has a much higher threshold value. It's going to get you up to, it's got a good life expectancy. But now, because of all that extra chrome and some of the processing techniques, you're up to 276 a pound for the base one. And if you get the higher strength level, you can get the price down a little bit. Once again, here you're not at the 75. You're not being as conservative as you are with the 75 with the 1035 bar. We're being done. So anyway, this is concrete. I mean, I felt pretty bad when I saw that, Mike, cement contents. This analysis was done a little before that. Usually we have it much lower than this now to get the paste fraction down, or they have to use an SRA or something to take count of that. But I mean, usually it'll be less, but this is an example. So whatever mix you want to put in there, you can do it, and it'll just change the curves a little bit, and you work accordingly. So that's the mix we use. These are the parameters from a stadium that we had. That too looks like it's a high number, but then it's multiplied by the porosity, and because it's on hydroxide, it actually ends up being a diffusion coefficient that's upper 10 to the minus 13 range meters squared per second. So it's the game. So it's not as it's just how the modeling handles it. So that's extremely good concrete, and you don't necessarily have to be that good. And then you can see we do that. We come up with chloride, percent chloride on the concrete on the y-axis, and the x-axis is years. And we have various lines. For the upper line is with 1 inch of cover, which of course nobody does, but then we go to 1.5 inches, 2 inches, and 2.5 inches, which are more common. The threshold line for stainless steel, and this is above the charts of stainless steel, would not be expected, and at least for this concrete in this time period. They have chloride above the threshold value. The threshold value for the A1035 9 is that upper line up here, and other than 1 inch of cover, which nobody would use, nothing. It's going to be way beyond chloride initiation. I have a line for galvanized here. Galvanized bar would get you up to about there, and then this line here is for the A1035 at 4% chrome. And here's your black steel, and epoxy has a longer. It has basically the same threshold value, but it goes out a little bit longer with propagation time. But I think as they found in Virginia, it's not going to get you much beyond 70 years, 75 years. Why time over the black bar? But if you want to get a bridge that's going to last 100 years, it's not necessarily going to do it, even with the higher covers. And as a designer, you can design cover. So I mean, you can see the advantages of getting cover as you bring these. As the cover gets higher, you can see that you get more. You have more stuff. More likely to be under the threshold level, moves farther out. The advantage of using the stainless and the 9% chrome is that even as this 1.5 inch cover here, if you use 2 inches cover, you got a little bit of safety factor. So that's I think that's one of the reasons for using that. Once again, we come to the actually looking at this on for this particular example, the black bar had 19 years with the propagation 25 years. The 4% chrome 43 to 61 with that, but once again you can increase cover in both of those and get a little bit better performance. And of course the high chrome and the stainless steel did much better. And you can actually look at the cost analysis on this. So you can see the black bar is up front, but now it was 75 cents a pound, but you have so much, you don't have 1 pound per square foot of bridge deck. So when you actually figure out how much you got in there, it's looking at it's got a low initial cost compared to everything, but your first repair is coming out there at a relatively early time, and you do a net present value cost analysis of what's it's worth in today's dollars, and it's $12.91, and you add up all the other repairs you have in that 100-year lifespan, and it ends up being $46 a square foot. The 1035 at 9%. With no taking advantage of that, comes out about the same price. But you didn't have any repairs in 100 years, so now you don't have traffic control and all the indirect costs that we have. And for those of you interested in CO2, your deck, everything lasts longer. You're using less CO2. The cars aren't sitting in traffic spewing out CO2. So altogether, you end up being significantly better off. And you can see as you go along, as you get higher and higher, if you take advantage of the strengths, the price gets even much less compared to that. And the stainless steel works, but it ends up still being more expensive. So that's that. Just conclusions, because I know Mike's looking at me, is that both you can have a lower cost of back bar when you use utilizing higher strength on the bridge design mix. I mean, you start adding user cost and traffic control, and both of these give a much, much lower cost than black bar. They could both beat 100-year service lives before major repairs would be needed. Once again, designers, if you can, think about this when you're doing your design. You'll save money, and I know at least one case where somebody did that. And the DOT thought it was innovative, and they actually went with that project. So something to think about. And both of them, and the main point here, as I mentioned this and not some of the other stuff, is that both of these are being used in Virginia to no small extent due to Mike's Mike. And that I say thank you, and I guess questions aren't now. So.